The tube itself, seemingly the simplest component, required precision manufacturing that challenged German industry. The 88mm steel tube had to be perfectly straight and uniform in diameter to ensure the rocket travelled true. Any variation caused the projectile to tumble or veer off course. The interior surface needed specific roughness too smooth, and the rocket might lodge too rough, and it created excess friction that reduced velocity. German steel mills rolled tube stock to exacting specifications, then machinists reamed and honed each tube to final dimensions. Quality control rejected approximately 8% of tubes for dimensional errors, a surprisingly high failure rate that reflected the precision required. Each tube then received a coating of zinc chromate to prevent rust, particularly important given that these weapons would see service in Russian mud and Norwegian snow. The sights evolved through several iterations during development. Early, prototypes used simple iron sights borrowed from rifles, but test firers complained that judging range and calculating proper aim was nearly impossible with such crude reference points. The rocket's trajectory was not flat like a bullet. It dropped noticeably at longer ranges, requiring the gunner to aim above the target. Engineers developed a ladder sight with range markings from 50 to 150 meters, allowing operators to adjust for distance. The trigger mechanism required surprising sophistication. It couldn't simply complete an electrical circuit like a battery-powered system. It had to drive the spring-loaded striker rod with sufficient force to generate ignition current, but not so violently that the impact jarred the gunner's aim. The mechanism needed to function reliably after exposure to mud, water, freezing temperatures, and the general abuse of infantry combat. German manufacturers produced several versions before settling on a design that balanced reliability with manufacturing simplicity. Even then, field reports would later note that the trigger mechanism was the most common point of failure, particularly in winter conditions, where lubricants congealed and metal contracted. September 8, 1943, marked a watershed moment. A German military report stated the weapon would be sent to frontline troops for trials sehr bald very soon. This wasn't quite true yet. Production was just beginning, and the first weapons off the line required extensive testing before anyone would trust them in combat. But the optimism was justified. Germany had transformed a captured American weapon concept into indigenous production capability in less than 10 months. By September 30th, the official manual for the Panzerschreck had been published and distributed to training units. The manual, designated D 2440/1, provided comprehensive instructions for operation, maintenance, and tactical employment. Unlike the Americans who deployed bazookas without training, German military doctrine demanded that every operator receive formal instruction before touching frontline weapons. The manual detailed loading procedures, aiming techniques, safety precautions, and malfunction drills. It specified that operators must wear gloves and protective goggles due to backblast danger. It warned that firing from enclosed spaces would kill the operator from blast overpressure. It recommended two-man teams with the gunner aiming and firing, while the loader handled ammunition and watched for threats. October 5th saw the first delivery of 1,500 weapons and 5,000 rockets to combat units. This was a trial distribution, sending Panzerschrecks to selected formations for field evaluation under actual combat conditions. The units were primarily on the Eastern Front, where the need was most desperate and where combat would test the weapon thoroughly. The transformation from captured American weapon to German mass production had taken less than 11 months from the first specimens arriving at Kummersdorf to finished weapons reaching soldiers. For a military bureaucracy often criticized for slowness and over-engineering, this represented remarkable speed. The production numbers revealed the scale of German commitment to the weapon. Initial orders called for 382,000 units, a staggering quantity that reflected how desperately Germany needed infantry anti-tank capability. Material shortages and Allied bombing would reduce actual production, but the ambition was clear. Germany intended to equip virtually every infantry unit with Panzerschrecks. By July 1944, when production of the original RPZ B-54 model ceased in favor of an improved version, 289,151 units had been manufactured. An additional 25,700 improved RPZ-B-54 models would be produced between December 1944 and the war's end, bringing total production to approximately 315,000 weapons. Manufacturing the Panzerschreck required just 10 work hours per weapon at a material cost of 70 Reichsmarks. To understand the significance, compare this to traditional anti-tank weapons. The smallest German anti-tank gun, the 3.7 cm Pak 35/36, cost 5,730 Reichsmarks and required a crew of 6 plus a vehicle for transport. The Panzerschreck cost 1.2% as much and could be carried by 2 soldiers. A single Panzerschreck cost less than a Mauser K98K rifle, which typically cost 80 to 100 Reichsmarks depending on manufacturing facility. Yet the rifle could only kill infantry. The Panzerschreck could destroy a 40-ton tank worth hundreds of thousands of Reichsmarks and crewed by 5 trained men. The economic efficiency made mass production feasible even as Germany's war economy contracted under Allied bombing and material shortages. The human cost of production remains one of the darkest chapters in the weapon's history, though it's rarely discussed in technical accounts that focus on engineering achievements. HASAG, one of the primary manufacturers, was the third largest exploiter of forced labor in Nazi-controlled Europe. The company operated multiple production facilities using slave laborers from concentration camps, prisoners of war, and civilians conscripted from occupied territories. By October 1943, over 60,000 workers labored for HASAG. More than half were forced laborers with no choice in their employment and no protection from abuse. The company operated 165 sub-camps by 1945, housing prisoners under conditions that routinely killed them through overwork, starvation, and deliberate cruelty. At HASAG facilities in Poland, particularly the Werk-Schlieben ammunition factory and associated camps, approximately 35,000 deaths occurred between 1943 and 1945. Incomplete records prevent precise accounting, and the actual number may be significantly higher. Workers endured 12-hour shifts with exposure to toxic chemicals used in explosive production. Beatings were routine for failing to meet production quotas. Rations provided barely enough calories to sustain life, and medical care was non-existent. The Schlieben camp, producing munitions including Panzerschreck rocket motors and warheads, housed between 2,000 and 5,000 female prisoners at various times. The average life expectancy at this facility was approximately 2 months. An explosion there on October 12, 1944, killed 96 prisoner laborers. German authorities made no attempt to rescue survivors or recover bodies. They simply brought in replacement workers and resumed production. Other HASAG facilities showed similar patterns. At Musselwitz, where Panzerschreck tubes and firing mechanisms were manufactured, forced laborers worked in unheated factory buildings through German winters. Frostbite injuries were common and untreated. Workers who collapsed from exhaustion or malnutrition were often shot rather than provided medical attention. The factory needed to maintain production schedules, and sick workers represented inefficiency. The Panzerschreck was an engineering success built partially on systematic murder. Modern accounts that celebrate the weapon's rapid development and technical sophistication rarely acknowledge that thousands of people died producing it, worked to death in conditions designed to extract maximum labor before disposal. Every Panzerschreck that reached German soldiers represented not just engineering skill, but human suffering measured in corpses, approaching 20-minute mark at approximately 2,900 words. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The weapon's combat deployment began in autumn 1943, initially in small numbers as production ramped up and training programs expanded. By January 1944, 21,141 Panzerschrecks had been issued to combat units. though another 39,526 remained in armories due to Wehrmacht distribution problems. The distribution system struggled with competing demands. Every infantry division wanted Panzerschrecks immediately. Eastern Front commanders, facing massed Soviet armor attacks, claimed absolute priority. Western Front units, preparing for the anticipated Allied invasion, demanded weapons for beach defense. Units in Italy, fighting up the peninsula against American and British armor, insisted their need was equally urgent. The Heereswaffenamt attempted to allocate weapons based on threat assessments and strategic priority, but reality often diverged from plans. Transport disruptions caused by Allied bombing meant weapons accumulated at depots while frontline units went without. Bureaucratic inefficiency resulted in some divisions receiving far more Panzerschrecks than their authorized allocation, while neighboring formations had none. By mid-1944, distribution had improved somewhat, though it remained chaotic. German tactical doctrine called for each infantry company to have at least 2 Panzerschreck teams, with additional weapons distributed at battalion and regimental level. Elite formations like SS Panzergrenadier divisions might have 6 to 8 teams per company. Reality rarely matched doctrine, but even partial distribution provided German infantry with anti-tank capability they desperately lacked. Eastern Front forces received priority for Panzerschreck distribution, reflecting the overwhelming armor threat they faced. Soviet tank production had reached massive scale by 1943. The Soviets built over 20,000 tanks in 1943 alone, primarily 34 medium tanks and various heavy tanks including KV series and the new IS-2 Stalin tank. German forces faced armor attacks of stunning intensity. Soviet tactics employed massed tank formations, sometimes hundreds of vehicles in coordinated assaults supported by artillery and infantry. German anti-tank guns, when positioned and supplied, could inflict terrible casualties on these attacks. But there were never enough guns, never enough ammunition, and Soviet attacks came constantly, grinding down defenses through attrition. The Panzerschreck gave German infantry a weapon they could employ independently, without waiting for anti-tank guns to arrive or friendly armor to provide support. A 2-man team hiding in rubble or forest could ambush Soviet tanks at ranges where the shaped charge warhead was deadly. The psychological impact on German infantry was immediate and profound. Soldiers who'd felt helpless against armor now had something they could fight with. Soviet tank commanders quickly noticed the changing tactical situation. Where German infantry had previously relied on magnetic mines requiring suicidal close approaches, anti-tank rifles that were marginally effective at best, and bundled grenades with tiny effective ranges, they now possessed weapons that could engage tanks at 150 to 200 meters under favorable conditions. Every German strongpoint potentially concealed multiple Panzerschreck teams. Soviet armor could no longer simply overrun German positions with confidence that infantry had no effective defense. The tanks needed infantry support to suppress Panzerschreck teams, artillery preparation to destroy positions before armor advanced, and reconnaissance to identify likely ambush sites. This forced Soviet forces to slow their attacks, coordinate combined arms more carefully, and accept higher casualties when armor advanced without adequate support. German commanders exploited this shift ruthlessly. The weapon proved particularly effective in defensive positions where German forces could prepare ambush sites with interlocking fields of fire. German tactical doctrine, refined through bitter experience, called for Panzerschreck teams to establish positions in staggered trenches no more than 115 meters apart, ensuring attacking armor-faced rockets from multiple directions simultaneously. Teams would dig shallow fighting positions with overhead cover to protect against artillery, camouflaged to blend with surrounding terrain. The positions included escape routes, narrow trenches, or natural depressions, allowing operators to withdraw immediately after firing. Standing to fight after revealing position by launching a rocket was suicide. Soviet return fire, whether from tank guns or supporting infantry, would saturate the launch site within seconds. The effective range against moving targets was approximately 100 meters, though static targets could be engaged at greater distances. The rocket's relatively slow velocity, 110 meters per second, meant that aiming at moving tanks required significant lead. A tank traveling at 15 kilometers per hour would move over 4 meters in the time the rocket traveled 100 meters. Gunners learned to aim ahead of their target, judging speed and distance by instinct developed through training and combat experience. Technical performance data from German and Finnish tests demonstrated the weapon's capabilities and limitations. The RPZB Granate 4322 rocket achieved penetration of 160 mm of armor at 60-degree impact angle, or up to 230 mm at optimal 90-degree perpendicular impact. These figures represented substantial improvement over the American Bazooka's penetration of roughly 75 to 100 mm. The rocket velocity of 110 meters per second compared favorably to the American Bazooka's 85 meters per second. The higher velocity meant flatter trajectory, slightly better accuracy, and reduced flight time that gave targets less opportunity to evade. The warhead contained 700 grams of explosive, triple the American weapon's charge. This larger explosive mass generated a more powerful shaped charge jet with greater penetration capability. Despite superior performance on paper, combat employment revealed persistent problems. The backblast remained desperately dangerous, despite protective equipment. Operators firing from trenches sometimes suffered severe burns when exhaust reflected off trench walls. In winter conditions, the blast could ignite dry vegetation or wooden structures, revealing position through smoke and flame. The weapon's signature bright flash, followed by distinctive smoke trail, made concealment nearly impossible after the first shot. The Blast Shield edition in February 1944 created the RPZB-54 model, which became the standard production variant. This shield, a curved steel plate mounted forward of the trigger assembly, protected operators from the rocket's backblast and reduced injuries significantly. The shield increased weight from 9.25 kilograms to 11 kilograms, making the weapon noticeably more cumbersome but far safer to operate. Operators still required protective equipment, including heavy gloves and face protection, as the backblast danger zone extended 10 to 30 meters behind the weapon, depending on terrain and weather conditions. Firing in snow created massive steam clouds. Firing in mud splattered debris across a wide area. Enclosed spaces remained absolutely prohibited. Firing a Panzerschreck inside a building would kill the operator from blast overpressure and anyone else in the room from concussion and fragmentation. Western Front deployment accelerated before D-Day as German forces prepared for the anticipated Allied invasion. Wehrmacht commanders in France received thousands of Panzerschrecks during spring 1944, positioning them to engage Allied landing craft and tanks at the waterline. The weapons proved effective in Normandy's bocage country, where short engagement ranges and abundant concealment suited Panzerschreck tactics perfectly. The bocage, ancient farmland, divided by centuries-old hedgerows growing on earthen banks, created natural mazes of confined spaces and short sight lines. Tank battles occurred at ranges under 100 meters, where the Panzerschreck was most deadly. German infantry teams could hide in hedgerows, wait for Allied armor to pass within effective range, fire from concealment, and escape through the maze-like terrain before Allied infantry could respond. American tank crews, recognizing their own invention turned against them, developed countermeasures with varying success. Tank commanders welded additional armor plates to hull, fronts and turrets, hoping the extra thickness would defeat shaped charge jets. It rarely worked. The Panzerschreck's penetration exceeded most improvised armor additions. Crews hung sandbags on hulls, believing sand would disrupt shaped charges. This proved somewhat effective, but added weight that strained engines and transmissions. The most effective countermeasure was aggressive infantry screening. American doctrine evolved to advance infantry ahead of tanks by 50 to 100 meters, suppressing Panzerschreck positions before armor came within effective range. This worked when terrain and tactical situations allowed it, but slowed advances significantly and exposed infantry to small arms fire without armor protection. Artillery and mortar fire targeted suspected Panzerschreck positions, saturating likely ambush sites before armor advanced. This preparatory fire consumed enormous ammunition quantities and was only partially effective. German teams could dig deep enough to survive artillery, and the Wehrmacht quickly learned to position Panzerschreck teams in sites that American observers wouldn't identify as likely positions. The psychological impact often exceeded the physical damage. Allied tank crews knew that every hedgerow, every pile of rubble, every seemingly innocent building might conceal a Panzerschreck team. The weapon's distinctive launch signature became a dreaded sight: bright flash, smoke trail, then the awareness that a rocket was inbound with less than a second to react. Tank commanders reported that crew effectiveness decreased significantly in areas known to have high concentrations of Panzerschrecks. Crews buttoned up, closing hatches and vision ports to protect against shaped charge jets. This reduced visibility drastically, making it difficult to spot Panzerschreck teams before they fired. Some crews preferred to keep hatches open despite the danger, accepting risk of injury to maintain situational awareness. Others stayed, buttoned up, and relied on supporting infantry to identify threats. Neither approach was satisfactory. The Panzerschreck had created tactical problems that Allied forces never fully solved. International proliferation began even before the war ended, demonstrating that Germany saw the Panzerschreck as both a weapon and a commodity with diplomatic value. Finland, fighting desperately against renewed Soviet offensives, purchased 1,854 launchers and 18,650 rockets for 200,000 Reichsmarks in 1944. Finnish forces achieved remarkable success against Soviet armor with Panzerschrecks. Finnish tests confirmed penetration of 100 mm of face-hardened armor at 30 degrees, sufficient to defeat 34 tanks at combat ranges. Finnish soldiers, already skilled at anti-armor tactics, from years of fighting technologically superior Soviet forces, integrated Panzerschrecks into ambush tactics that inflicted disproportionate casualties on Soviet tank formations. The Finns modified German tactics for their particular environment. They positioned Panzerschreck teams in frozen forests, where Soviet tanks channeled into predictable routes through snow and trees. Teams would engage from ranges under 75 meters, targeting side and rear armor, where Soviet tanks were most vulnerable. After firing, Finnish teams would withdraw on skis, moving faster through snow than Soviet infantry could pursue on foot. Hungarian forces received Panzerschrecks for Operation Spring Awakening in March 1945, Germany's last major offensive of the war. This desperate attack near Lake Balaton in Hungary attempted to secure Hungarian oil fields and protect Germany's southeastern flank. The offensive failed within days, crushed by overwhelming Soviet superiority in numbers and firepower, but Hungarian units equipped with Panzerschrecks destroyed dozens of Soviet tanks in the fighting. Allied intelligence closely monitored the Panzerschreck phenomenon with growing concern. A British intelligence report from January 1945 noted that German production of nearly 300,000 units in 18 months exceeded total Allied bazooka production during the same period. This was remarkable considering that Germany was losing the war, suffering under constant strategic bombing, and facing critical shortages of almost every material needed for weapons production. American ordnance experts studying captured Panzerschrecks recognized that the Germans had identified and corrected every significant weakness in the original M1 bazooka design. The magneto-ignition eliminated battery problems. The larger warhead provided superior penetration. The improved rocket motor extended range and velocity. Even the problematic backblast, while dangerous to operators, was an inevitable consequence of superior performance. The German rocket generated more thrust and burned longer, creating the backblast but also delivering better terminal effects. The Americans themselves adopted German improvements for later bazooka models, essentially reverse-engineering the reverse-engineered weapon. The M9 bazooka, introduced in October 1943 shortly after American forces first encountered Panzerschrecks, incorporated magneto-ignition similar to the German system. This eliminated the battery problems that had plagued M1 bazookas in North African cold nights and Italian winter mountains. The M20 Super Bazooka, developed late in the war but not fielded in significant numbers before Germany's surrender, increased caliber to 3.5 inches 89 mm, nearly identical to the Panzerschreck's 88 mm. This larger warhead followed the German example of using larger-shaped charges for better penetration. The M20 would go on to serve in Korea, where it proved highly effective against Soviet-built 34 tanks, the same vehicles the Panzerschreck had been designed to destroy. Production statistics reveal the weapon's importance to German strategy and the industrial commitment required to sustain manufacture. By July 1944, when production of the RPZ-B-54 ceased in favour of improved models, 289,151 units had been manufactured. Monthly production peaked at approximately 15,000 units in early 1944, before Allied bombing disrupted supply chains and reduced output. Each weapon required components from 32 subcontractors, demonstrating the industrial complexity behind what appeared to be a simple tube launcher. The tube itself came from specialized steel mills. The firing mechanism required precision machining of electrical contacts and spring assemblies. The sight system needed optical components and adjustment mechanisms. Even seemingly simple parts like the shoulder stock and blast shield required specific materials and manufacturing processes. This distributed production network proved both resilient and vulnerable. Resilient because Allied bombers couldn't destroy the entire system by hitting any single facility. Vulnerable because disrupting any critical subcontractor could halt final assembly. The Heereswaffenamt maintained elaborate tracking systems, monitoring component flows, identifying bottlenecks before they stopped production, and redirecting resources to maintain output. Allied strategic bombing increasingly degraded this system through 1944 and into 1945. Attacks on transportation networks disrupted component deliveries. Strikes on steel production reduced raw material availability. Bombing of chemical plants limited explosive and propellant production for rockets. Germany's entire war economy contracted under this pressure, yet Panzerschreck production continued at reduced levels through April 1945, just weeks before surrender. The improved RPZ-B-54 model, introduced in December 1944, addressed remaining deficiencies identified through 18 months of combat experience. The tube length shortened from 164 centimeters to 135 centimeters, making the weapon more maneuverable in confined spaces and easier to transport. The reduction came from improved rocket design that achieved full velocity in shorter acceleration distance. Engineers developed improved rocket propellant that burned more efficiently, generating equivalent thrust with less material and significantly reduced backblast. This made the weapon safer for operators and reduced the distinctive launch signature somewhat, though it remained obvious to anyone nearby. The refined sights incorporated lessons from combat, with clearer range markings and improved adjustment mechanisms. Despite orders for 48,000 improved RPZ-B-54 units, only 25,744 were delivered before Germany's surrender in May 1945. The final months of production occurred under impossible conditions, factories operating without electricity, workers labouring under constant air raid alerts, transportation systems so disrupted that components sat at depots while assembly facilities ran out of materials. Engineers also developed prototypes using impregnated cardboard tubes to save steel, desperately scarce in the war's final months. The cardboard tubes, treated with special resins to handle launch stresses, theoretically could function for several shots before degrading. Testing showed mixed results. Some tubes worked adequately, others failed catastrophically on first firing. None reached production before the war ended, but the concept demonstrated how desperately Germany was scraping for alternatives to conventional materials. Cost-effectiveness analysis demonstrates why Germany prioritized Panzerschreck production even in the war's final desperate months. Each weapon cost 70 Reichsmarks and required 10 work hours to manufacture. The smallest traditional anti-tank gun, the 3.7 cm PaK 35/36, cost 5,730 Reichsmarks, and was ineffective against modern Allied and Soviet tanks anyway. A single Tiger tank cost approximately 300,000 Reichsmarks when factoring in all production expenses. For the price of one Tiger, Germany could theoretically produce over 4,000 Panzerschrecks. The Tiger was undeniably more powerful, but it required months to build, consumed massive quantities of scarce materials, needed a trained crew of 5, and was vulnerable to mechanical breakdown. The Panzerschrecks could be distributed across hundreds of infantry units, providing broad anti-armor capability rather than concentrated firepower in a few elite formations. This economic calculus drove German strategy in the war's final year. As tank production collapsed under bombing and material shortages, the Wehrmacht increasingly relied on infantry anti-tank weapons, Panzerschrecks, and the single-use Panzerfaust to provide defensive capability against overwhelming Allied armor superiority. It was a strategy born of desperation but grounded in practical mathematics. Germany couldn't match Allied tank production. They could produce infantry weapons in massive quantities and hope that sheer numbers of Panzerschrecks could offset armor disadvantage. Ammunition production matched weapon manufacturing in scale and complexity. Over 2 million rockets were produced during the war, primarily the RP's-B Granate 4322 model, with its distinctive streamlined shape and fin stabilization. Each rocket weighed 3.3 kilograms, complete with warhead and propellant. The rockets came packaged in wooden crates of 2, with each crate weighing approximately 8 kilograms, including packaging. Special winter and summer variants accommodated temperature extremes that affected propellant performance. Winter rockets used propellant formulated to burn reliably at -30 degrees Celsius. Summer rockets were optimized for temperatures up to 40 degrees Celsius. Using the wrong variant in extreme conditions could result in dangerously unpredictable performance, underpowered rockets that fell short, or overpressure conditions that damaged launch tubes. Transport frames allowed soldiers to carry 5 rockets in addition to the launcher itself, though the combined weight of approximately 27 kilograms limited mobility significantly. Panzerschreck teams typically couldn't keep pace with rapidly moving infantry. They were defensive weapons, positioned ahead of anticipated enemy advances, or employed in deliberate attacks where infantry moved slowly and carefully. The logistical burden of rocket supply created constant challenges. 2 million rockets distributed across hundreds of divisions meant approximately 5,000 to 7,000 rounds per division over the weapon's service life. This sounds substantial until considering combat consumption rates. In intensive defensive fighting, a well-supplied Panzerschreck team might fire 10 to 20 rockets per day. A division holding a threatened sector could exhaust its entire stock within weeks. The ammunition supply system struggled to keep pace. Rockets were bulky and heavy, requiring truck transport to forward depots. Allied air superiority made daylight movement suicidal in Western Europe from mid-1944 onward. The Eastern Front saw somewhat better supply conditions, but vast distances and poor roads limited delivery capacity. Units frequently reported having Panzerschrecks but insufficient ammunition, rendering the weapons useless decorations. The weapon's influence extended well beyond World War II, shaping anti-tank weapon development for decades. Belgian company Mekar, which had produced Panzerschrecks under license during German occupation, developed the blindicide RL 83 inches, the 1950s, using similar principles. This weapon maintained the 83mm caliber close to the Panzerschreck's 88mm and employed comparable shaped charge technology. The Swiss Army adopted derivatives as the 8.3cm rocket-propelled grenade, maintaining upgraded versions in service through 1980. Swiss engineers improved the propellant and warhead design, but retained the basic concept of a shoulder-fired tube launching shaped charge rockets. The weapon saw no combat use in Swiss service. Switzerland maintained armed neutrality throughout the Cold War, but its long service life testified to the soundness of the underlying design. The basic concept of an oversized shaped charge in a shoulder-fired tube influenced anti-tank weapon development worldwide through the 1950s and 60s. American weapons designers studied captured Panzerschrecks extensively, incorporating lessons into weapons that would serve through Korea and Vietnam. Soviet designers did likewise, though Soviet weapons development followed somewhat different paths, emphasizing recoilless rifles alongside rocket launchers. Post-war analysis by American ordnance experts acknowledged German achievements with remarkable frankness. Colonel C.T. Richards wrote in a 1946 U.S. Army Ordnance report that the Panzerschreck program represented history's most successful reverse engineering project, achieving mass production in under 7 months from initial specimen capture. Richards noted that Germans had taken a hastily developed American weapon and transformed it into a mature system that exceeded the original in a measurable performance metric. The report detailed specific improvements: magneto-ignition versus battery power, 88mm versus 60mm caliber, improved propellant formulation, better sights, more robust construction. Richards concluded that American designers should have developed these improvements themselves before deploying the M1 Bazooka, acknowledging that the weapon had been rushed into combat with inadequate development. Soviet forces captured thousands of Panzerschrecks during their advance into Germany, shipping examples back to ordnance evaluation centers for study. Red Army technical reports noted the weapon's superiority to captured American bazookas received through Lend-Lease. The Soviets had initially rejected American bazookas as insufficiently powerful, receiving only approximately 3,000 units with minimal ammunition through 1944. The German version, with its larger warhead and greater penetration, better suited Soviet tactical requirements. Soviet doctrine emphasized close-range infantry combat in urban and forest environments, where the Panzerschreck's characteristics were optimal. Soviet engineers studied captured examples, but ultimately developed indigenous designs, the RPG series that would become ubiquitous in Cold War conflicts rather than directly copying German technology. The last documented combat use of wartime Panzerschrecks occurred during the 1948 Arab-Israeli War, when Syrian forces employed captured German weapons against Israeli armor. These Panzerschrecks had traveled from German factories through various conflicts and changing hands multiple times, demonstrating the durability of the basic design even after years of storage and rough handling. Some examples remained in Third World arsenals into the 1960s, long after more advanced anti-tank weapons became available. These weapons typically came from stocks abandoned by retreating German forces in 1945, captured by advancing Allies or Soviets, then sold or transferred through murky international arms markets to various factions and governments. That Panzerschrecks were still considered viable weapons 15 to 20 years after manufacture testified to their robust construction. Technical documentation survived in remarkable detail, providing modern historians and weapons researchers with comprehensive understanding of the system. The Wehrmacht's September 30, 1943 manual, designated D2000, 440/1, provided extraordinarily thorough instructions for operation, maintenance, and tactical employment. The manual ran to 73 pages with detailed diagrams showing every component and procedure. American intelligence translated captured manuals within weeks of acquisition. An October 7, 1944, U.S. Army report titled German Hollow Charge Rocket Launchers, detailed German firing procedures, aiming techniques, and safety requirements based on captured documentation. These translations reveal the thoroughness of German training programs despite wartime pressures and resource constraints. The manual specified that operators must complete minimum 40 hours of training, including classroom instruction on weapon theory, practical handling exercises, and live fire qualification. Operators fired at least 10 practice rockets at various ranges before certification for combat duty. This stood in stark contrast to American soldiers receiving bazookas in North Africa with no training whatsoever. Safety statistics highlight the weapon's inherent dangers, even with trained operators. German records indicate numerous operator casualties from backblast injuries, premature rocket detonations, and enemy return fire attracted by the weapon's prominent launch signature. Exact casualty figures are impossible to determine. German casualty records from 1944 and 1945 are incomplete or lost, but after-action reports frequently mention Panzerschreck operators killed or wounded during engagements. The 10 to 30-meter backblast zone behind the weapon required careful positioning to avoid injuring friendly troops. Infantry advancing with Panzerschreck support needed training to maintain proper spacing. Multiple accounts describe German soldiers killed by friendly Panzerschreck backblast when they positioned themselves too close behind firing teams, unaware of the danger zone. Urban combat proved particularly hazardous as backblast reflected off walls, creating overpressure conditions that injured operators even when they followed safety protocols. Soviet forces fighting through German cities reported finding dead German soldiers near Panzerschrecks in circumstances suggesting backblast injuries in confined spaces. The weapons were devastating in urban combat but desperately dangerous to their own operators. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.